In this deck, we focus on a core coordination problem inside a modern automated container terminal. How to dispatch automated guided vehicles so container moves stay smooth and continuous, while also managing battery charging so vehicles do not fail mid-job. Dispatching is not just picking the nearest vehicle. It is a sequence of real-time commitments that affects quay crane productivity, yard congestion, and truck service at the gate. The key complication is energy. Every automated guided vehicle runs on a finite battery. A route that looks efficient can become useless if a vehicle drops below a safe battery level before finishing a pickup and drop-off. So the operational goal is to balance two needs at once. Keep tasks moving with minimal waiting, and schedule charging proactively so you avoid breakdowns, charger queues, and too many vehicles leaving service at the same time. Imagine an automated terminal where automated guided vehicles move containers between quay cranes, yard stacks, and truck loading zones. The terminal behaves like a tightly coupled system. If vehicles arrive late at the quay, cranes wait. If vehicles arrive late at the yard, stacking delays propagate. If vehicles arrive late to trucks, gate queues grow. This is why dispatching feels like the pulse of the system. You need the right vehicle at the right place at the right time, repeatedly, as new transport tasks arrive. And because the fleet is battery-powered, you also need charging decisions that keep the fleet healthy without turning the charging stations into a new bottleneck. We tackled the problem through a tiered toolkit, moving from rigorous modeling to practical real-time control. Tier 1 builds a mathematical vehicle routing formulation with time windows and battery constraints. Tier 2 uses a battery-aware cheapest insertion heuristic for fast dispatching. Then we expand to more powerful approaches. Tier 3 uses anti-colony optimization to explore better routing patterns. Tier 4 uses deep reinforcement learning to learn dispatching and charging behavior in a dynamic environment. Tier 5 introduces an integrated digital twin. Tier 6 uses a multi-agent system with contract net-style task allocation. Tier 7 adds a human control tower with explainable decisions. Tier 9 reframes a simplified version as a quadratic, unconstrained binary optimization model for quantum optimization. Tier 1 models the terminal as a network of locations and tasks and treats each automated guided vehicle as a resource that must travel, perform service, and consume energy. The model chooses travel arcs, tracks arrival times, and tracks battery levels, so feasibility is enforced step by step rather than assumed. Operationally, this formulation forces you to make the hidden constraints explicit. You cannot promise a pickup at a certain time if travel and service time would push you outside the allowable window. And you cannot promise a route if the battery would dip below the minimum safe level before the vehicle reaches either a task node or a charging station. This slide defines what the nodes are in the routing model. You have pickup nodes where a container is collected, drop-off nodes where a container is delivered, charging station nodes where energy can be replenished, and a depot or idle location where vehicles start and end. The reason sets and nodes matter is interpretability and correctness. If the model does not distinguish pickup and drop-off properly, it can generate sequences that are impossible to execute. If charging stations are not represented as real nodes, the model cannot schedule charging stops in a way that is consistent with the rest of the route. Parameters describe the real-world environment the model must respect. Travel time between nodes captures how long it takes to move through the terminal. Energy consumption between nodes captures how battery drains with distance and motion. Time windows define when service is allowed or required. You also need service times because arriving is not the same as completing a pickup or a drop-off. And you need charging rates for each station because charging is not instantaneous. These inputs are what make the routing model operational rather than purely abstract. Decision variables represent the choices the model makes. The routing choice indicates whether a particular automated guided vehicle travels from one node to another. Time variables represent when a vehicle arrives at each node. Battery variables represent the battery level upon arrival. You also need a charging time decision when a vehicle visits a charging station. That is how the model can express how long should the vehicle charge here. As a controllable decision, rather than forcing every charge to be either full or none. The objective in this formulation is to minimize total travel time across all automated guided vehicles. Minimizing travel time is a good proxy for efficiency because it reduces empty movement and tends to reduce congestion and waiting. But it is important to understand what the objective is not doing. It does not automatically guarantee good charging behavior. Charging behavior becomes good because the constraints enforce safe battery limits and feasibility, and the model is forced to include charging stops only when needed and only when they can be executed in time. Time windows enforce that service happens within allowed time limits. In practice, this protects against two failure modes: arriving too early when the task is not ready, and arriving too late when the task has become urgent and delays propagate to cranes or trucks. When you apply time windows to pickup and drop-off nodes, you ensure that routing decisions respect operational commitments. This is especially relevant when many tasks compete and the terminal is congested, because small delays can cascade into large losses of throughput. Time propagation is the physics of the schedule. If a vehicle arrives at one node, then spends service time there, and then travels to the next node, its arrival time at the next node must reflect that full sequence. This constraint prevents a common modeling cheat, pretending a vehicle can teleport between tasks or overlap actions in time. With time propagation, every route becomes a consistent timeline, which is essential if you want the solution to be executable. Battery consumption ties movement to energy. Every time a vehicle travels from one node to the next, it must spend energy, and its battery level must decrease accordingly. Operationally, this prevents paper routes that look short on time but ignore the energy reality. If the solution sends a vehicle on a long detour while its battery is already low, this constraint will make that route infeasible unless a charging stop is included. Battery charging models the opposite effect. When an automated guided vehicle visits a charging station, its battery level can increase based on the charging rate and the time spent charging. This constraint is where you connect dispatching to battery management. It forces the planner to account for the fact that charging takes time, chargers have capacity limits in reality, and charging decisions trade off immediate availability against future reliability. Battery limits enforce safe operation. The battery level must remain between a minimum safe threshold and a maximum capacity. The minimum threshold is crucial. It protects against the catastrophic failure mode where a vehicle runs out of power mid-job and blocks lanes or interrupts crane service. The maximum capacity matters too because it prevents wasting time overcharging beyond what is physically possible. This slide shows the network view of the problem: nodes for pickups, drop-offs, charging stations, and the depot, connected by travel arcs. Use this picture to build intuition. A good solution is not just a list of tasks, it is a path through the network that respects time windows and energy limits. The route may include detours to charging stations, and those detours must be justified by feasibility and overall efficiency. Consider the small example described here: 2 tasks, a single charging station, and 1 automated guided vehicle. The tasks are pick up 1 to drop off 1, and pick up 2 to drop off 2. The vehicle starts with a full battery. The key idea is feasibility over the entire route. The planned sequence must complete both tasks while ensuring the battery never drops below the minimum safe threshold. If the direct route cannot do that, the route must insert a stop at the charging station at the right time and for the right duration. Tier 2 shifts from exact modeling to real-time practicality. Instead of solving a full vehicle routing model repeatedly, the heuristic builds routes incrementally by inserting new tasks into existing routes. The battery-aware part is not optional. When the heuristic evaluates an insertion, it checks whether the modified route remains feasible under the projected battery levels. If it is not feasible, it considers inserting a charging stop and reevaluates the cost. This slide highlights the evaluation logic. You compare inserting a task directly into the route versus inserting it with a detour to a charging station. Operationally, this is the decision trade-off you face constantly. Direct insertion is usually faster if it is feasible, but if direct insertion pushes the battery below the safe limit, the heuristic must account for the charging detour, including the extra travel and the time spent charging. In the first part of the pseudocode, focus on the loop structure. You keep a list of unassigned tasks, maintain current routes for each vehicle, and repeatedly pick the next task to assign. Then, for that task, you try possible insertion points across available vehicles. The goal is to compute the incremental cost of each candidate insertion, while tracking whether the resulting route remains feasible in both time and battery. In the second part, the heuristic handles feasibility and commitment. If a candidate insertion isn't feasible because of battery, the method tries a charging insertion and recomputes the cost. Finally, it commits the best feasible option, the vehicle and insertion position that yields the smallest cost increase. This is what makes the method deployable. It is fast, it updates routes online, and it has a built-in safety check against battery failure. Tier 3 uses ant colony optimization to search for higher quality routing patterns than a simple insertion heuristic can typically find. The method builds candidate routes by simulating many ants, each constructing a route through tasks and charging stations. The choice of the next move is probabilistic and is influenced by learned memory, called pheromones, and by greedy desirability, such as shorter travel time. Battery state is tracked so that infeasible routes are penalized, and charging moves become more likely when battery is running low. This slide is about how the next step probability is formed. Pheromone memory captures what worked well in previous iterations, and heuristic desirability biases the search toward moves that look locally efficient. Operationally, this gives you a balance between exploitation and exploration. You exploit good historical patterns, but you also keep exploring alternatives, which is important in routing because there are many local optima, and small early choices can have large downstream effects. This visualization summarizes the ant colony optimization cycle. Ants build routes, solutions are evaluated, and successful routes reinforce the pheromone trails. Think of pheromone reinforcement as learning from experience. Over iterations, the algorithm increases the chance of selecting route segments that repeatedly appear in strong solutions, while pheromone evaporation prevents the search from getting stuck too early on a suboptimal pattern. In the first part of the pseudocode, focus on initialization and route construction. You initialize pheromones, create a population of ants, and for each ant, you build a route step by step. At each step, you choose the next node based on the probability rule and update the ant's simulated state, including remaining tasks and battery level. This is where battery awareness must be explicit. Otherwise, the algorithm will generate routes that look attractive, but are infeasible. The second part covers solution evaluation and pheromone updates. After ants finish constructing their routes, you compute route quality based on cost measures, such as total travel time and feasibility. Then you apply evaporation to reduce all pheromones and apply deposition to strengthen pheromones along good routes. Over many iterations, this feedback loop concentrates the search around better dispatching plans while still allowing occasional exploration. Tier 4 reframes dispatching as sequential decision-making in a dynamic environment. A deep reinforcement learning agent learns a dispatch policy that trades off task completion against battery health, rather than solving one static optimization instance. The slide lists the kind of information that matters: vehicle locations, battery levels, pending tasks, charging station queues, and congestion. Actions include accepting a task, going to charge, or waiting idle. Rewards encourage completing tasks quickly, penalize idleness when tasks exist, and penalize falling below a critical battery threshold. This slide shows the reinforcement learning interaction loop. The agent observes the state, takes an action, receives a reward, and transitions to a new state. Operationally, the key benefit is adaptation. The agent can learn to anticipate congestion, time windows, and charging station queues, and it can learn policies such as charging early to avoid a future queue or delaying a low-priority task to preserve battery for urgent work. Tier 5 introduces a digital twin, a synchronized virtual replica of the terminal that evolves in real time with the physical system. It supports monitoring, what-if simulation, and optimized control. This is valuable because you can test decisions safely before applying them. For example, you can evaluate adding charging stations, changing dispatch rules, or adopting a new policy. And you can measure impacts on throughput, wait times, and charging congestion without disrupting live operations. This slide visualizes the digital twin ecosystem for automated guided vehicle operations. Think of it as a closed loop. Sensors and operational systems feed state into the twin. The twin runs analytics and optimization, and decisions are sent back to guide dispatching and charging. The practical outcome is faster learning and safer change. Instead of guessing whether a new dispatch strategy will help, you can compare strategies under realistic conditions and deploy only when the evidence supports it. Tier 6 moves away from a single central dispatcher. In a multi-agent system, tasks are broadcast, and vehicles bid for tasks based on their own state, such as distance, battery level, and deadlines. This creates decentralized coordination. It can scale well as fleets grow, and it can be robust to partial failures. Charging can also be negotiated by querying station queues and expected wait times, leading to emergent coordination rather than a single top-down plan. This architecture slide highlights the contract net and Blackboard-style task allocation. Tasks are posted, agents evaluate, bids are submitted, and a task is awarded. Operationally, the bid is a compact explanation of how suitable am I for this job right now. A vehicle that is close and has high battery can offer a low expected completion time. A vehicle that needs charging soon can either bid high or decline, protecting the system from assigning tasks that will fail. Tier 7 keeps humans in the loop. Instead of manually dispatching every move, humans supervise the autonomous system through a control tower dashboard. The dashboard supports high-level goals, explainable reasons for actions, and exception handling. The system can detect anomalies, diagnose issues like a vehicle stuck or congestion forming, and recommend interventions that a human can approve when risk or value is high. This slide summarizes the workflow. The automation handles routine decisions, provides explanations and alerts, and escalates when it detects abnormal situations. Operationally, this design combines speed with accountability. You get the efficiency of automation, but you also maintain oversight for safety, customer priorities, and rare edge cases that require human judgment. Tier 9 reframes a simplified assignment problem as a quadratic, unconstrained binary optimization problem. In this framing, costs appear as linear terms, and constraints are enforced by adding quadratic penalty terms. The intuition is simple. Feasible assignments have low energy because they satisfy penalties, while infeasible assignments have high energy. A quantum annealer-style solver then searches for the lowest energy configuration, which corresponds to a low-cost assignment that respects the constraint penalties. This slide focuses on the objective term, a cost for assigning a specific vehicle to a specific task. In practice, that cost can reflect travel time, energy consumption, or a combined operational estimate. The key point is that the objective term is where efficiency enters the model. If you define costs poorly, you will optimize the wrong behavior. If you define them well, the optimization naturally prefers assignments that reduce delay and wasted movement. This slide introduces the penalty that enforces each task must be assigned exactly once. Without this penalty, the optimizer could assign no vehicle to a task or assign multiple vehicles to the same task to reduce cost artificially. Operationally, this penalty protects completeness and avoids duplication. It encodes the rule that every task must be covered, and covered by one and only one vehicle. This slide presents a capacity-style penalty, such as each vehicle can perform at most one task, in a simplified assignment version. This is not meant to be the full reality of routing. It is a controlled simplification that makes the quadratic unconstrained binary optimization framing easier to solve. The penalty ensures you do not overload a vehicle in the simplified model and that the assignment remains internally consistent. Here we combine the objective term and the penalty terms into one full quadratic unconstrained binary optimization expression. The important practical point is calibration. The penalty weights must be large enough that violating constraints is never worth it compared to reducing cost. If penalties are too small, you get cheap but infeasible assignments. If penalties are too large, the search can become numerically difficult. This slide visualizes the structure of the quadratic, unconstrained binary optimization matrix. Diagonal entries represent linear costs, while off-diagonal entries represent interactions that enforce constraints. Use this as a mental model. Costs tell you which individual assignments are attractive, and interactions tell you which pairs of assignments cannot coexist without penalty. The matrix is the data structure that a quantum annular style approach uses to search for the best configuration. The first practice set focuses on Tier 1 and Tier 2 thinking. For Tier 1, you consider a scenario with 2 automated guided vehicles and 1 task, where the travel time from the depot to pick up one is 10 minutes for the first vehicle and 12 minutes for the second vehicle. You practice writing the objective and the single task assignment constraint in the same style used in the formulation. For Tier 2, you practice the insertion decision. When a new high-priority task arrives, evaluate direct insertion into an existing route versus insertion with a charging detour. The point is to make you articulate the feasibility check and the cost comparison, not just the intuition. This set focuses on handling invalid solutions and reward design. For Tier 3, consider what happens when a route constructed by an ant would deplete battery before all tasks are completed. You practice describing how the method should penalize that solution and how that affects pheromone reinforcement over time. For Tier 4, you practice proposing a reward function that rewards task completion but penalizes battery depletion and idleness. The goal is to show you understand the behavioral incentives. If you reward only completion, the agent may take risky actions. If you penalize only time, it may avoid necessary charging. This set is about design and economics. For Tier 5, you design a what-if scenario to evaluate purchasing 5 new faster-charging automated guided vehicles. You also specify which metrics you would measure, such as throughput, average task waiting time, charging station queue time, and the frequency of low battery events. For Tier 6, you practice describing the bid a vehicle would submit when a task is far away, but located near a charging station the vehicle needs soon. The bid should reflect a trade-off. Distance makes the task unattractive, but proximity to a needed charging stop can make the combined plan more reasonable. This set connects human oversight and quantum-style penalties. For Tier 7, interpret an alert about task starvation in Zone C in 45 minutes. Task starvation means that work in that zone is at risk of being ignored or delayed because vehicles are being pulled elsewhere, which can create a service collapse later. You then propose 2 high-level commands that a human could give to mitigate the risk, such as prioritizing that zone temporarily or reallocating a portion of the fleet. For Tier 9, you practice writing a penalty term so one automated guided vehicle can do at most one of 2 tasks, ensuring the expression is 0 when the rule is satisfied and positive when it is violated. To close, remember the core message. Automated guided vehicle dispatching is a coupled routing and energy management problem. If you optimize only dispatching, battery failure can break operations. If you optimize only charging, you can remove too many vehicles from service and slow down throughput. The tiers form a progression of capability. Heuristics provide speed, meta-heuristics improve quality, and deep reinforcement learning adapts online. Digital twins and multi-agent coordination improve resilience and scalability, and quadratic unconstrained binary optimization formulations provide a roadmap for future acceleration under simplified modeling assumptions.